Okay, so here we have an RC circuit, and at t equals 0, this circuit is closed, and it's going to charge this capacitor over here. The battery holds an EMF of 20 volts. Here we have a resistor of 10 mega ohms and a capacitor of capacitance 5 microfarads. So for part A, we want to figure out how long will it take for the charge on the capacitor to reach 3.92 microcoulombs. So to figure out the charge on a capacitor in an RC circuit, we have to use this formula. Q equals the capacitance times the EMF of the battery times 1 minus e to the minus t over RC. So we want to figure out how long it'll take the charge on the capacitor to be 3.92 microcoulombs. So we want to solve for t. So let's divide out by CE, Q over C epsilon equals 1 minus e to the minus t over RC. Can rearrange this and get e to the minus t over RC equals 1 minus q over c times epsilon. And if we take the natural log of that, we'll just get minus t over RC equals natural log of 1 minus q over c epsilon, right? Because the natural log of e to something is just that thing. And just multiply by negative t over RC, and we've solved for t minus RC ln 1 minus q over c epsilon. Okay, now plugging in our numbers, let's see. R, the resistance is 10 mega ohms, so that's minus 10 times 10 to the 6 ohms times our capacitance, which is 5 microfarads, so that's 5 times 10 to the negative 6 farads, times ln of 1 minus, our charge is 3.92 microcoulombs, that's times 10 to the minus 6, over 5 microfarads times our EMF, which is just 20 volts. And if you plug all that in, you should get approximately 2 seconds. All right, so in part B, we want to figure out what is the potential difference across the capacitor at that time. The time being what we just found, which is t equals 2 seconds, when the charge on the capacitor is 3.92 microcoulombs. So to find the potential difference, we can just use our formula for capacitance. C equals Q over V. If we rearrange that, we get V equals Q over C. So we know the charge on the capacitor, and we know the capacitance of the capacitor, so let's just plug that in. Charge is 3.92 microcoulombs times 10 to the negative 6 over 5 microfarads, again 10 to the negative 6, and we get a potential difference of 0.78 volts. Okay, so now for part C, we want to figure out how much energy is stored in the capacitor when it has a potential difference of 2 volts. So one of the formulas for the potential energy in a capacitor is U equals Q squared over 2C. But now we don't actually know the charge on the capacitor. We only know the potential difference across it. So we're going to have to calculate that charge. And we can do that using this equation. Capacitance is charge divided by the potential difference. Rearranging for charge, we have Q equals CV. Now we can plug this into our equation for the energy over here. So we have U equals CV squared over 2C, which is just equal to CV squared over 2. And now we can just plug in our values. We have a capacitance of 5 microfarads. It's 10 to the negative 6 times. We have a potential difference of 2 volts. So that's going to be 2 squared over 2. And that is going to give us 10 microjoules of energy.